Right. So in this part of this video, we will see about some important aspects like event signals, what is debug, and what is rescue DP and other things. Right. So to start with event signals, before getting into this event signals, there are certain other things which we are supposed to know. See, when you take a microcontroller has its own power requirement, right? If you take a simple, very common Arduino, it runs in 16 megahertz, and it requires, for example, let's say it uses 50 milliamperes of current. We have our RP2040. The processor itself is around 160 sorry, 133 megahertz speed. It is that fast, and it has Wi-Fi, it has Bluetooth. So when all this is turned on, the RP2040 can easily consume somewhere around 200 milliamperes. Now if I have a sensor connected to it, if I have an actuator, it can easily lock up to 300 milliamperes, right? So this is way too high. So if I run RP2040 with these sensors connected to battery, let's say I'm connecting 3.7 volt battery with 3000 mAh, what will happen? Simple math, 3000 mAh, 300 milliamperes per time. So it will the entire system will not work for more than 10 minutes or maybe lesser than that, right? So what we have is, we have something called as event, right? So this is where event signals comes into the play. So this particular microprocessor Cortex M0 Plus, it can enter into a state called as sleep state. So when it goes to sleep state, everything will be um, everything else will be in sleep mode, so that the amount of power consumption will be very high, right? So we call this as a sleep mode, and then this sleep mode, everything will be in sleep except for very few hardwares present inside that particular microcontroller setup, right? And if there is something, if there is some action to be taken, for example, if the sensor senses something and the motor or some other actuator is to be turned on, at that instant what happens is, the wake for event signal is sent. So this is WFE, which is wait for event. So that is sent, and it creates or it triggers the microcontroller, and the microprocessor system backs into action, and then everything starts working, and it will continue with its operation, right? So while it is in this sleep state, the processor can shut off its internal clock gates, consuming less than zero point 0.2 milliwatts, which is very 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 important, because when you for example, let's take this scenario. You have a automatic water controller system in play. Let's say there is a overhead water tank in your house, and we have a special setup, a sensor setup. The sensor will continuously measure the water level, and when the water level goes down, your microcontroller has to turn on the main water pump, which will pump the water from the base storage unit to the overhead tank. Now for that setup, if you keep your microprocessor, your sensors and actuator setup, everything on for continuously, the battery will die, right? Uh, if you plug it to AC power supply, that's different. But still, plugging AC power supply, taking wire to the overhead tank, all those are going to be a little difficult, and it is not that practical. So people will often prefer battery powered system, or maybe in few cases they can have small solar panel. So whatever the situation it is, when a microcontroller, it is not necessary to measure the water level every 5 minutes. Okay, the water level change in 5 minutes is not going to make a big deal. So what you can have is, I can set a timer for 30 minutes, and only at a regular interval of 30 minutes, the sensor will turn on, will check the water level, turn off. If the water level is 90%, I can even set the timer to 2 hours, or even 6 hours or 3 hours, depending on the tank. So all these hours, when the alarm time is, the microcontroller can be put into a sleep mode. That way the power can be conserved, so that your microcontroller, the life of the microcontroller, the battery power of the microcontroller, the usage, everything can be extended over a long period of time, right? So this is the advantage of having a event signal, right? Now into the debug. Debug, as we all know, is uh, debugging. as simple as it, right? So here we have already seen that the main architect in the main architectural diagram, so ignore it. So we saw something on the extreme top right. So it had something like this. You have core 0, core 1, and from that there was a wire directly connected towards the end. So that is actually DAP, or you can simply write debug. When I say DAP, it is it's okay, it's not actually DAP, it is debugging. There they would have mentioned SW, serial wire debugging. So what they're saying is I can directly talk to my microprocessor. We are actually talking about microcontroller, but for debugging I can directly talk to the microprocessor and see how it is being performed, right? So if it is like writing the main firmware to the SRAM, or if I want to set breakpoints in my microcontroller and to see how the program, the firmware is working to a particular level, to run, to halt, and to other functions that is available in these ARM controllers, I can perform that. I can directly access the processor's architecture state. I can see how the memory to other memory input output device is being connected, how the address is being done. Everything I can debug using this particular what do you say, facility, or this particular option, right? So each DAP, we have seen DAP in SIO, right? That DAP will respond to the debug commands if correctly addressed. If you should have some kind of address, or you think it's available in the next slide. Yeah, okay, so this is not exactly debug, but it's a rescue operation. Okay, so in this rescue DP, if you enter this word, if you give this command in the go to this register, and if you give some value, it will rescue your system. For example, if the code that we have written has some problem, and it if it permanently resets the system, every time it turns on, it automatically restarts, turns on, automatically returns. So that is a kind of hang situation. The chip gets locked up. So in that situation, this will come into the play, and it will restart the system. And what you see here is the software control of SWD pins. So you can see what are the different things that we can do. I'm reiterating this again. The bits, name of the register, the description, the type and reset to be seen again properly. So here most of them are read and write. Only certain things are read only. So what is read only? In that you can only read and see the status. We cannot update it, right? So description, so you can see that in this particular debug GeForce register, you can directly control the SWD port of either both the processor. So if you want it to be on the processor 1, you have to use this. On processor 2, this. So this here also you can see the description. So processor C1 attach processor 1 debug controls and disconnect from the. So everything, each and every operation that you can perform can be actually seen, modified and controlled by this registers. There are so many other registers beyond this. You can explore it from the data sheet, and you can learn.